just wanted to suggest one of those elements that we thought would be critical for the steering committee to be aware of.
Absolutely required information. Thank you, Doctor. We go on. So just to give a
ايه يا امي ها يلا يلا
companies to review it from a linguistic point of view, from a
الرجاء كنت جاءت لي كم قال سوا
Good afternoon, everyone. This is Asma Milibari from the ASA Research Group at KU, welcoming all of you again to the third lecture of the Machine Learning short course titled The Reinforcement Learning, presented by the distinguished professor, Dr. Vineet Agrawal. So welcome, Dr. Vineet, and welcome everyone else. Before we begin, I just would like to remind everyone that, as usual, your questions and comments regarding the topic are welcome during the lecture. You can either speak or use the chat option. And we thank Dr. Vineet for taking the time to answer them. So, Dr. Vineet, we can start now.
Thanks a lot for the introduction, and thanks everybody for attending. So this is the third lecture for reinforcement learning. In the last lecture, we introduced the concepts of policies, value function, and the Q function. Just a brief reminder on the three terms. We defined the policy as pi, A given S, which is the probability that the agent takes a decision A or takes an action A in the state S. This is the key objective that we want to find in decision making. In order to quantify how good the policy is, we define the value function. In order to define value function, we first define the reward, the return the reward is instantaneous and the return is a future reward, which was defined as sum over gamma k r t plus k plus 1 from k going from 0 to infinite. The value function v pi in state S is expected value of gt given you are in this state, and the q function is characterized by state and action, which is expected value of gt given state is S and action is A. So this was where we stopped in the last lecture. Any questions so far? Okay. So these are the two terms that we have to find for a given policy to figure out how good one policy is compared to the other. So last time we mentioned 3 of the steps. First question that we are going to answer is how to evaluate the value and Q functions of a policy. Okay. So in order to understand that, let us go into one of these equations. So evaluation. And the key reason is expected value over pi gt would take a lot of evaluations directly by definition. So you cannot really compute them just by definition. So we have to go a step forward. So by definition, v pi s is expected value of gt given st equals s. Then I expand the definition of gt, which is given by equation 1 here. If you notice, I can take the definition of gt, and the first term is rt plus 1 corresponding to k equal to 0. Gamma to the power 0 is 1. So I can write this as rt plus 1. And then I take gamma outside, and the rest of the term is rt plus 2 plus gamma rt plus 3. And if you notice, that term is nothing but gamma gt plus 1. So I took the first term and left the remaining as gt plus 1 in the equation 1 here. Is this step clear? Okay. So when we have gt plus 1, we actually need to know what happened in the time t plus 1. We need to know the state of t plus 1. How would we find the state of t plus 1? So you were in the state S. The transition probability to time t plus 1 for the state will need also what was the action taken in time t to compute the entire expectation. So we will need two things to sum over. First is, what is the action you took? So when I've summed over A and inside is A, that means I took action A at time t. Then I need to figure out which state did you go in the next time. So let us say you go to state S prime, and I'll sum over S prime and R because I know the transition probability as P S prime R given S comma A. So in each of the term, I have taken action A at time t, and I have reached state S prime at t plus 1. I have obtained reward R at time t, and in this conditioning, my gt is rt plus 1. Rt plus 1 in this case is R because I received the reward R. And plus gamma expected value over pi GT plus 1. Rather than conditioning over S, we have gone to S prime because of Markov property. If I know S prime, it doesn't matter what S was. So I could write as ST plus 1 equals S prime. Is this conditioning step clear? So what I kind of did was I conditioned it over the action you took at time t, which is A, and then summed over that. And then I conditioned on the next state and next reward being S prime and R. Is this step clear?
Yes.
Thanks. So can somebody tell me what is this term? Look at the definition of V pi S. If you notice at the definition of V pi S, that is time independent. So time index of t or t plus 1 should not matter. So what is this term?
Going to be a V pi
Of
S prime.
yes. So this is V pi of S prime. So we'll substitute this and get an equation. So we have V pi of S is summation over A pi A given S summation of S prime R P S prime R given S and A R plus gamma V pi S prime. Okay. So given that we got this type of equation for V pi, how do you think we can solve this? How can we compute V pi SS? We already know the policy. We already know the transition probability. Okay, we can already observe the rewards in the different states and actions. Any ideas? So these are a set of simultaneous equations. So you write down all the equations for each of the S and solve using the number of states linear simultaneous equations. Is that clear? So this equation is called Bellman equation. Okay. The reason R is known is because we are summing over. So R is not really a variable. Gamma is known. So only thing that is unknown here is V pi. So you'll have simultaneous equations in terms of different V pi's. So similarly, we can get this form of equation for Q also. Q pi SA is, so methodology is the same. So I'll just write down the steps. Given ST equals S, AT equals A. This is, only thing is, since I'm known action, I'm not summing over the policy. So I only have to do the inside sum, which is sum over S prime and R. P S prime R given S A R plus. To go to the next state, we will have summation over A. Since you already have A, this would be A prime for the next time, comma. So we are doing this A prime because in the next, to get the GT plus 1, we will need the S prime as well as A prime. So in order to get S prime and A prime, we are doing the conditioning over action at time t plus 1. Probability of A prime given S prime, expected value of over pi, GT plus 1 given ST plus 1 is S prime and AT plus 1 is A prime. Can you see how this term would come? Directly using exactly the same step. And again, this term is Q by S prime A prime. So we have this as summation S prime R P S prime R given as A R plus gamma summation A by A prime given S prime Q by S prime A prime. So this equation is called Bellman equation for Q function. And that was Bellman equation for V function. Any questions at these equations?
No.
Okay, so you can take any example among the ones that we did before. In the first case, you will have number of equations being the number of states. In the second one, you will have number of equations being the number of states times the number of actions. And you can try to solve these linear equations to get your answers. Okay, so in this lecture, we will not go over detailed evaluation, but since these are very simple linear functions, you could take any random policy and evaluate them. Okay. So now we discussed about performance of any policy. Okay. We also need to talk about optimal policy. Given the performance of any policy, any ideas how we can find the optimal policy looking at these equations? So you are given, let me ask the question more precisely. I'm given a policy pi. Can you come up with a better policy than policy pi to improve the policy to get something better? So V pi is summation over A pi A given S. I need to maximize V pi where pi is my variable. What should my pi be? So if we have to find the optimal pi, looking at this equation of V pi S, okay, I need to maximize V pi S. What should I set my pi to be? It is linear in terms of pi. It is sum over A with the probabilities. So let us say for each A, I have terms inside. So let me give you an example to make it more clear. So let us say you have only two actions given a state. So you have V pi S equals pi A1 given S1, some function of A1. Sorry, no S1, just S here. Plus pi A2 given as f of A2. Okay, what would be my optimal policy? Can you find me these terms if I have to maximize V by S? Okay, so can V by S be larger than max of f of A1 and f of A2? Is the inequation clear? Because pi's are between 0 and 1, FAIs are non-negative. Can you get a configuration where V by S can be larger than any of the FA1 or FA2? Larger than the max of the two? Okay, let us say this is 3. Let us say this is 4. Can V by S be larger than 4? By choosing pi's?
I don't know. Maybe. I don't know. Maybe if it's pi 1 and pi another one is 1, so 3 plus 4 is 7. But I'm not sure.
Okay, the sum of probabilities
Yes.
of different actions given a state is 1.
Yeah, I know.
So if it is 1, can you choose any configuration and cross 4? So 1 and 1, the sum is 2.
Yes.
I want the sum of them to be at most 1.
Okay, so half and half. No, it's not going to be more than 3 and 4. No.
Yeah, it cannot be more than 4. So
Yes.
the maximum V pi that could happen will be the max of the two terms. And what is the probabilities I should use to achieve that? If I have to achieve 4, what would be the values of the probabilities? Zero and 1, right? So in order to achieve 4, I have to set this probability as 0 and this probability as 1, right?
Yes.
So that is exactly what I'll do to find the optimal policy. So in each state, I choose the action which corresponds to the maximizing of the sum inside. So that is the key intuition that we will use to find the optimal policy. Okay. So we denote the optimal value function V star S as the maximum over the policy V pi S, and similarly Q star S comma A is defined as max over the policy Q pi S comma A. The policy that maximizes both the functions can be proved to be the same. We are not talking about uniqueness. The optimal policy may not be unique, but the set of optimal policies in the two are the same. So now we have to come up with equivalent of Bellman equations for V star and Q star to be able to find these in closed form. Okay, so as you just noticed, if you know the Q star or V star, you will know the optimal policy too, because if you look at the definition of Q pi or V pi, in V pi, the action that maximizes the inside term, as we just saw from the example, is the optimal policy. And same for the Q pi. You have, for a given state, the A that maximizes Q pi SA is my optimal policy. So those are the intuitions that I will use to find the optimal policy. But in order to find that, we first need to find V star and Q star. Okay, so P star of S is maximized over A, Q pi star of S comma A. So the optimal value function is based on the optimal Q function for the policy pi star, which is the optimal policy. So pi star is the argmax. So the action that maximizes the Q function. Okay. So this is max over A, expected value pi star, R t plus 1 plus gamma G t plus 1, the definition of Q function, given ST equals S and AT equals A. Okay, so I now have to take the expected value, the policy inside. So this is max over A, expected value over RT plus 1 does not depend on policy anymore. The expected value over pi star of GT plus 1 is nothing but V star. The state, however, is the next state. Given ST equals S, AT equals A. So this is max over A. Since this is ST plus 1, I have to go to the next state. So this is sum over S prime and R, P, S prime and R given S comma A. R plus gamma V star S prime. So these are pretty much the same steps. Only difference that we did was the action has to be the maximizing action. So we removed the summation over A. In the previous one, we had summation over A pi A given S. And in the optimal policy, so in the V pi S, we were doing the summation over A pi A given S. And in the optimal policy, we know that only one of those pi's could be 1 corresponding to the best one. So using the equation here of maxes, we basically replace that sum over A pi A given S by the maximizing action and change the policy from V pi to V star. So those are the two differences in V star compared to V pi. Any questions for this?
No.
Okay, that's great. So now we have equation for V star. Could you evaluate V star for a given example? Again, you have set of equations for each S. The main challenge here is this max. So the equations do not remain linear. However, you are still finding a fixed point solution. Okay, so you could, in theory, use these nonlinear equations to find the fixed point. The way we did the equations for V star, we could also do them for Q star. Rather than doing the entire detail, I'll just write the answer. Summation S prime and R P S prime. The approach is exactly the same. Rather than using sum over pi, we will use the max over A. because the optimizing action will take the entire weight in the optimal policy. Okay, so the same approach, you have a equation for Q star with the max here rather than summation over pi a prime given s prime, and that will give you the optimal policy. Okay, and you already know the optimal policy. If you are given, if you can find all the Q star SA, the A that maximizes Q star SA in a given state is my optimal policy. All right. So the steps to do if you have to find the optimal policy is first find Q star SA and then choose the action A that maximizes Q star SA when you are in state S. Are the steps clear for the optimal policy?
Yes.
Okay. So there are some examples in the chapter 3. So feel free to go over the examples to see how these equations look like for them. And with that, we are done with the chapter 3 of the textbook. So we'll now briefly work over chapter 4, which is going more deeper into the same set of equations for the optimal policy to see algorithmically solving this fixed point is not an easy job. How can we make the computation of the optimal policy easier? Okay. So even when we described the steps, the first step that we used was policy evaluation. What was policy evaluation? The policy evaluation was I have to find V pi of S for a given policy. Okay. So in order to compute that, we came up with the equation, which is this set of simultaneous equations. Okay. So if you have to write an algorithm for this, how would you do that? How would you write an algorithm to come up with a fixed point solution for this? And the answer is very simple. It's a standard numerical algorithm that we typically use for solving the fixed point. So in each time, we find V pi, the current estimate on the left-hand side, using the previous existing estimates for the right-hand side. So we don't solve the simultaneous equations. So how many of you remember the Newton's method and other numerical methods that to solve fixed point equations? So if you have an equation, x equals f of x, and you have to find the fixed point solution, you basically, in order to do that, you basically do xt plus 1 equals f of xt for t equals 1 to so on. So if you do this, you will eventually get up into the fixed point. Okay, so xt plus 1 is assigned f of xt. So essentially, if you keep on doing f of, and you will reach the fixed point solution. And the key intuition is fn of x equals fn plus 1 of x, which is what this is saying for every n, and eventually I will get there. So do you remember this approach of doing the fixed point solutions?
For me, no, I don't remember.
Okay, but is the approach clear?
Yes.
Okay, so this is typically how in numerical literature we solve the fixed point equations, and we'll kind of use the same approach. So so we repeat again and again for each state. We define value function of state based on the sum over a pi a given as summation s prime r p s prime r given as a r plus gamma b prime s, where the right hand side was what was learned before. So that is essentially what we will keep on doing, and we will keep updating till you are doing a significant change. So you will have repeat until you are seeing a significant change in the value functions across the iterations. So that is a numerical method to achieve the fixed point solution of the equations. And the next step is, so this is, as I mentioned, policy evaluation. So this is going back to a numerical method for solving the particular equation of V pi s. Okay, so now we have the capability of solving V pi s numerically. The next step is to improve the policy. So we are given a policy, we have to improve the policy. And improvement of policy will still use the same approach. So to improve the policy, if the previous policy is pi a given s, in the new policy, we will, rather than using the summation a pi a given s, like in this equation of Vs, we will just use the max over a. Okay, so, and the action will be the argmax. If we just make that small change to change the policy to argmax, we will get a better policy. Okay, however, that better policy will still need the value functions, which is based on the original policy. So given a V, we can come up with a better policy of pi a given s, finding the argmaxes. So you have a original policy. Then steps are find value function, which is policy evaluation. Then step is improve policy. And to improve the policy, what you do is pi of state S is doing the maximum in that step. Argmax over A, the inside term, summation S prime and R, P S prime R given S comma A, R plus gamma V S prime. Okay, if your actions have stabilized, stop there. Otherwise, keep repeating. Find value, improve policy, and keep repeating till you get a convergence. Is the approach clear?
Yes, thank you.
So this algorithm is called policy iteration.
I have a question, please.
Sure.
For the last sentences, is it pi of s or v of s?
This equation is pi of s.
Pi, okay. Thank you.
Yeah, because we are doing a argmax.
Mhm.
Argmax means the action that maximizes the inside.
Okay. But it's the pi, it's with s and a, the action, or only the s, the state without the action?
Okay, so pi of s returns the action.
Okay.
And that action is the argmax action. So
Okay.
basically what this is meaning is pi a given s will be 1 corresponding to the one that maximizes this and 0 otherwise.
Mhm. Thank you.
Any other questions? Okay. So those of you who know dynamic programming, this approach is also called dynamic programming by doing this argmaxes. Okay. So next algorithm that we will consider. So, okay, before we go over algorithm, what is the downside of this particular algorithm? Does this algorithm seem good to use? The main challenge here is that finding value function or the policy evaluation step is not the optimal strategy, of course, because we are doing iterations. We are going over time in order to be able to compute it. So we first have to find a convergence here and then improve the policy, then again wait for convergence, then again improve the policy. So you have to wait for convergence infinite times. Okay, so every time you change the policy, you have to wait for the value function to converge in a lot of steps. Does that kind of make sense? So what we need is somehow combining the compute of value function as well as improving the policy together rather than they being separate. Okay, because finding value function will take a lot of time and we don't want to keep on repeating the times after we keep on changing the policy. So an approach to that is do both these type of things together, and the approach we'll use is called value iteration. And in order to understand that, we will directly use the V star equations. So we had the V star equation here. Rather than computing V pi, we could directly go at V star computations, which have already taken the policy into account. Okay, and we already give you a set of equations for V star. So like we have the corresponding equation for Q star. We also had, okay, I remember where it is. Here it is. So V star equation had been written in max over A. So we will use this equation to basically do the V star, and that will give me the value iteration. So repeat, we of course have to repeat things till convergence. Then for each S, we find Vs as, and this V is actually, we are doing the fixed point equation for V star directly. Max over A, summation of S prime and R, P S prime R given S comma A, R plus gamma B S prime. And until convergence. Okay. So convergence is of course by a threshold. So in numerical, you never converge to with the gap of 0. So you'll always have some threshold for convergence. So what we did was we directly estimated V star using the same fixed point solution approach. Now, after finding V star, we can find a policy. The optimal policy will be pi s is argmax over A of QSA. But QSA we have to find in terms of V's, which is easy. You only have to condition over the next step or the action here. Summation S prime R P S prime R given S A R plus gamma V S prime. So the same equation as above, we are finding the policy that is argmax of the same term as we are doing in the previous one. So the A that maximizes the above is my policy. So this is easy to do because we are directly computing V star, and then based on the convergence of V star, we are finding the optimal policy pi star. The good thing about this compared to the policy iteration is that we are only doing convergence once. So in the policy iteration, we were waiting for the convergence for each of the policy. And then after we update the policy, we were again computing the value of the policy. Here we are only doing it one time. Any questions? Okay. Do you feel confident taking this particular algorithm, for example, and implementing this for a particular scenario? Like one of the example we did before. Or do you see any challenge here? Any comments?
No.
Okay, so what do you think are the challenges in implementing this? Can you do it for some of the example like what we did last time?
Maybe, but I'm not sure.
Okay, so think of that as a homework and see if you can take this particular algorithm and code this up. You can choose any language that you like.
Okay, in which example exactly? I think we took 2 examples or 3. I don't remember exactly. But
so there was one example where we evaluated the P S prime R given S comma A.
Okay.
So can you take that example and see how what would be the optimal policy for that particular example?
Okay.
Okay. So the good or bad thing about this is a numerical approach. So means you would only understand it by coding. In theory, of course, you can, as I gave you the ideas, you can prove that since you're waiting for convergence, you will get into the fixed point solution, and every fixed point solution is optimal, which essentially means you will converge to one of the optimal strategies. Okay. Another point to note is when we define the pi of A given S from a theory perspective, the policy could be stochastic in terms of it may not be giving weight to one deterministic action only, which is what we are doing here. However, what we can show is this deterministic policy is also one of the optimal policies. So even though there is we are not saying every optimal policy is deterministic, but we are saying this deterministic policy is optimal, and there may be other probabilistic strategies that can achieve the same answers. And a side result of that is when you're doing this max over A, the max may not be unique. So if you have 100 actions, 5 actions may give you the same maximum value. However, it will not matter. You can give weight of 1 to any one of the action, or use any probabilities to give weights to only those 5 optimal actions. Everything will still be optimal based on the theory. Okay, so only thing I'm saying is this argmax may not be unique, and you can choose any one of the maxes or even assign any probability summing to 1 to those different values that maximize it.
Excuse me, I have a question.
Sure.
What are the best programs are used to do policy iteration?
What are the best what?
Best programs.
What do you mean by that?
I mean, if the computation are complicated, and so we need to use a program, right?
Yeah, so typically people do not implement policy iteration mainly because of doing this convergence many times. And that was the essential reason why we went over value iteration.
Okay.
So policy iteration was given as one of the basic methods. You can compute the policy, improve it, but if we already know the dynamic equations for the optimal policy, there is no need to go 2 steps. So value iteration in that sense is more efficient. But of course, even for policy iteration, there are improved algorithms. So what you kind of do even in policy iteration is that rather than waiting for convergence, you only do a limited number of steps there. So if you, for example, you choose that I do only 5 steps for policy evaluation and then do policy improvement, then do again 5 steps of policy improvement, policy evaluation, and so on. Those, of course, are computationally fine and you can implement it.
Okay, thank you.
Any further questions? Okay. The next question that we are going to think about is, now we have to take these, take the problem to the next scale. In this, we are assuming, if you notice all the equations, that the transition probability P S prime R given as A is known. Okay. There may be a large scale system, and these probabilities may be dynamic or time varying. So it may be hard in general to learn these probabilities, because in systems where you don't know much about the model, you have to estimate these transition probabilities. So the next question or a thought that we are going to think about, we won't solve it in this lecture, is P S prime R given as A is not known a priori. So if it is not known a priori, what are the approaches that you can use? So there are two things. First is what we call as model-based approach, which is saying that you can estimate this term using any Monte Carlo or basically frequency counting based approaches, and then use the above approaches. Or there may be more approaches, of course. Those are only examples. Second is model free, where you do not estimate P S prime R given as A and directly estimate Q function. So if you can directly estimate Q functions or update Q functions, then I might still be fine, right? Because eventually I do not, okay, we use small q. So if I can directly estimate Q, then I do not need to know the values of P's. So that is the model free approach. And we will talk about this model free approach in the next lecture. So the topics for the next lecture will be model free approach, and the other challenge in many of these problems is that we are assuming that it is a finite state space. However, in practice, the state space may be very large, and finding the Q functions for every state, if assume that the state is a real number, not even finite. So if it is a real number, finding Q function for every state is impossible. So we have to use some form of function approximators type of thing to get there. So that is the other thing that we will do. Scalability to large space, large state space. So in the inverted pendulum or the cardboard problem that we considered, the state space, if it includes what degree you are, how far are you from the top, how many angles of movement is there, the number is actually a real number. It is not a discretized degrees. So we want to be scalable to have examples like that. Of course, you can discretize, but that's not always the best. So we will basically study what are the best function approximators and things that you can use to have your algorithm scale to large state spaces. So just to give brief background, if you go over the technologies of reinforcement learning, the approach that did beat the best chess players back 20 years back were the standard model free approaches that we'll talk about. And the algorithms that recently did beat the AlphaGo Pro 4 or 5 years back were the scalable algorithms, because if in games or in any other environments, the state space becomes really large, you need some scalable algorithms. And one example to that is what we will do in the next time, deep Q learning, which will use neural networks as function approximators. Okay, any final questions?
Thank you, Dr. Vineet, for today's lecture.
Thanks, everyone.
Okay, does anyone have a question? Okay, I think no one has a question. So thank you again. It was a very informative lecture, and we will make sure to look over the examples as you mentioned. Okay, there's a question in the chat.
Yeah, slides, I would also like to have them. I don't know how to get them in the, there's also no options for me to save. Let me see. Oh, I found something to save. Yeah, the homework essentially is implement value iteration for any example. Yeah, I think I was able to download it. I will send the slides to Adele, who can forward it to you, or if there is another person I can email it to who can forward it, because on Zoom there is no send attachment link.
Okay, thank you.
But I think the Zoom session is being recorded, so the recording should be available somewhere, or you can ask Adele to see where the recording is.
Yes, so I will check with Dr. Adel about this, and we will let you know.
Okay,
okay.
Thanks.
So thank you, Dr. Vineet, and thank you, everyone. And we will see you in the next lecture next week on Monday, the 20th of July. Thank you.
Thanks, everyone.